In this video, we are going to solve a rigid Euler buckling problem. And as you can see in our problem statement, we're given the values for all of our spring stiffness coefficients, and we are asked to find what the critical load, axial load, is on the system in order to buckle the system. So the first thing we want to do with a problem like this is redraw with a free body diagram with forces of the springs and maybe the moment from the spring, because at the bottom we have a torsion spring. We want to draw our free body diagram as if it's been buckled. So I'm going to go ahead and draw just the basic free body diagram right now. So here is what our free body diagram would look like for this problem. We have exaggerated the angle that the bar is going to buckle, just so that we can fit all of our variables in. So the first thing we want to find is we're going to find all of our distances in our problem. So L and A are going to be given, so we don't have to worry about finding those. And so the next things we want to solve for are D1 and D2. And then theta we're just going to keep as theta. So for D1 and D2, we are going to use the small angle theorem. And this basically says that the sine of any angle is just going to be approximately equal to the value of that angle itself. So using that, we're going to come up with our distances. So for D1, that means our distance is going to be A times theta. And for D2, that means our distance is going to be L times theta. So now that we have all of our distances in our problem, we can go ahead and solve for our forces, our spring forces. So we're going to ignore the reaction forces at the bottom, since that's where we're going to take our moments about in the end. So first we're going to go ahead and solve our spring forces. So we'll start at the very top with our force in spring K3. And so if you remember from Hooke's law, a force is equal to its stiffness times the distance that it changes. So for our force in K3, that's going to be equal to the stiffness, which is K3, times D2. So if we plug in D2, we get that FK3 is going to be equal to K3 times L times theta. So if we do the same thing, force in K2, that's going to be equal to K2 times D1, which is equal to K2 times A times theta. So now the only thing we have left to solve is for our moment. So you can use Hooke's law again for this, but instead of stiffness times deflection, it's going to be stiffness times the total angle of twist that the spring, that torsional spring, has gone. So to figure out MK1, that's just going to be equal to its stiffness, K1, times theta, which is that angle that torsional spring rotates. So those are going to be all of our forces and then all of our distances. So now that we have all of those values, we can go ahead and take a moment from our support, our pin support. So if we go ahead and do that, I'm going to switch colors real quick. So if we do that, we can say sum of the moments at the pin is going to be equal to 0. I'm going to assume that clockwise is the positive direction for moments. And so if we do that, we get that if we look at the top force first, force P acting over a distance of D2 that's going to be in the positive direction. This is going to be minus our FK3 times L, that's the distance it acts over. Also another minus FK2 times A, and then minus our moment at the bottom, which is MK1. All of that's going to be equal to 0. So then we just go ahead and plug in what we know for those values. So we have P times L theta, which is D2, minus, and then our FK3 happens to be K3 times L times theta times another L, minus K2 times A times theta times another A, and then minus our MK1, which happens to be K1 times theta, which is all equal to 0. So if you look at this equation, each term has a theta, so we can go ahead and cancel the theta out of the entire equation. And if we do that, and rearrange it to solve for P, we get that P is going to be equal to K1 over L plus K2 A squared over L plus K3 times L. And so that's going to be our final equation. Then we just plug in all the values that were given in the problem statement. And when you do that, you should get a force, a P critical, of 974 pounds. And that's our final answer. And that's how you solve this rigid Euler buckling problem.